The assessment for internal validity is much more involved. There are a lot more things we need to consider before we can conclude with confidence that we have established the causal effect for the population being studied. To argue that you have established the internal validity for your study, you have to convince your readers that the estimator of the causal effect should be unbiased and consistent. Moreover, you have to show that the hypothesis test should have the desired level of significance at 10% level, 5% level, or even 1% level. Proving to your readers that the estimator for your variable of interest is unbiased and consistent is equivalent to proving that the first least squares assumption, that is the expected value of u given the axis is equal to 0, holds. Because if the first least squares assumption does not hold, then the estimator for your variable of interest is definitely biased. Generally speaking, there are 5 different sources of bias that will potentially lead to the violation of the first least squares assumption. If we have any of these five problems in our regression, then the estimator for the variable of interest is biased. Therefore, before you can declare that you have achieved the causal effect for your study, you have to consider whether any of these 5 problems are present in your regression. We had previously covered the first 2 sources of problems in the previous lectures. We talked about the omitted variable bias in Module 2 and the wrong functional form in Module 3. But we haven't discussed the remaining 3 problems: the errors in variables bias, sample selection bias, and the simultaneity bias. Next, we'll go over all of these 5 problems one by one in the following slides. The omitted variable bias arises when we omit a control variable that is the determinant of y, and the control variable is also simultaneously correlated with our variable of interest. To fix the omitted variable bias problem, we have to add all the valid control variables back in the regression. The problem is that some of these valid control variables cannot be measured, and therefore we have no way to include these control variables in the regression in order to completely remove the omitted variable bias. For example, in the California schools example, we want to know what is the effect of classroom size on test scores. One of the important determinants for the test scores is the internal drive for students. Specifically, we want to know whether students are curious, determined, and hardworking. Students with these internal characteristics tend to be associated with higher test scores. However, empirically, it's very difficult to measure the internal drive. That means we won't be able to remove the extent of the omitted variable bias associated with these internal drive characteristics because they are hard to measure. Hence, at the end of our analysis, the estimator for the class size is still biased. And that's why after this class, you're going to move on to study the panel data analysis. Panel data allows us to observe the same individuals over time. And assuming the characteristics of individuals are inherently stable, then we can use techniques to control for the inner characteristics of each individual over time in a panel data regression. Alternatively, we can also use the instrumental variable regression to correct this problem if certain control variables cannot be measured. The IV regression will be covered as the last topic of this module. Another idea to control for omitted variable bias is by running a randomized controlled experiment. Again, this approach is used extensively in political research, but it's not suitable for us. We, as social scientists, only use observational data, and therefore it's impossible and sometimes even unethical for us to use randomized controlled experiments in our analysis. For example, it's not feasible for us to randomly assign students to a control group versus a placebo group and see whether students in the control group who are placed in a smaller classroom have on average higher test scores. The design of this experiment involves playing with human lives and therefore should be strictly prohibited. The wrong functional form also leads to biased estimates for the coefficient. The way to fix the functional form is by adding polynomials, logs, or interaction terms to allow the linear model to fit the nonlinear data better. In the case where the dependent variables are discrete, we have to either run a probit or a logit if the dependent variable is binary, or use the multinomial logit regression if the dependent variable has multiple discrete values. Now let's pause this video to do in-class exercise 1 through 4. Another source of bias stems from the measurement errors in the x variables. We call this source of bias errors in the variables bias. So far, we have assumed that our observational data does not contain measurement errors, but in reality, economic data often contains measurement errors. The measurement errors could stem from data entry errors in administrative data. If you had a typo in entering the data manually, this typo becomes a measurement error. Or it could stem from recollection errors in surveys. For example, for consumer pricing index or CPI that is published every month is based on the household surveys, through which households are randomly chosen to fill out a very long questionnaire that includes questions such as, how much did you spend on gas last month? It's normally that some families cannot remember exactly how much they spent before, and they will fill out a rough number in the survey. This recollection error is a source of measurement error. The measurement error could also stem from ambiguous questions. If the survey participants cannot understand exactly what this question is asking for, naturally they couldn't provide an accurate answer to the question. In other cases, the questionnaire might be asking some sensitive questions that are considered personal, such as how much alcohol and drugs you're consuming and how much did you earn last year. Some folks might not feel comfortable giving the truthful answer to these questions, and as an alternative, they will intentionally lie about it. The forcefully reported numbers will be another source of measurement errors. Now let's look at the mechanism of how these measurement errors enter our regression and induce bias to our estimates. Say if the proposed model is a simple one-variable regression, where the x variable is measured imprecisely. Instead of obtaining the true x, we only can observe tilde x, which is based on the reported data. Therefore, the slope parameter beta 1 is obtained by regressing y on tilde x, whereas the true x becomes a part of the regression residual, denoted v. If v and tilde x are correlated, that means x minus tilde x is correlated with the tilde x, and then the expected value of v given tilde x is not equal to 0, and hence the first least squares assumption is violated. Consequently, the estimated beta 1 hat is biased and inconsistent. That's how the errors in the variable bias is induced. Let's break down the errors in the variables bias case by case, depending on how the errors were introduced. The first case of the errors in the variable bias is the most severe. We call it the classical measurement error model. Suppose that we don't know what is the mechanism for the errors to enter our data. In this case, we assume that the difference between the observed x and the true x is random. The difference is denoted by w, which follows a normal distribution with mean 0 and the variance equals to sigma w squared. Because w is random, the correlation between w and the true x is equal to 0. And the correlation between w and the regression residual u is also 0. It can be shown that in this case, beta 1 hat can be approximated using the variance ratio times the true beta 1. The variance ratio is computed using the variance of the true x in the numerator divided by the sum of the variance of x and the variance of w in the denominator. Since the variance terms are always non-negative, this ratio is therefore bounded between 0 and 1. If this variance ratio is very close to 1, that means the variance of w is very small, then beta 1 hat is very close to the true beta 1. On the other hand, if this variance ratio is very close to 0, that means the variance of w is very large. Then beta 1 hat computed as this ratio multiplied by beta 1 is going to be very close to 0. In this case, we say that the variance of the measurement error w attenuates the estimated beta 1 hat. Because if the variance of w is large, it attenuates the estimated beta 1 more. If the variance of w is small, it attenuates the estimated beta 1 less. Therefore, we call this type of errors in the variables bias attenuation bias. Again, this is the most problematic case of the measurement error, because in this case, we can prove that the measurement errors cause bias on the estimated beta 1. The second case is called the best guess model. This is a case when the results of the survey reflect best guesses. The observed x or tilde x is now a best guess. You can think of tilde x as a discrete value that lies either above or below the actual x. In this case, it's easy to see that the measurement error as defined by the true x minus tilde x should be uncorrelated with the discrete value tilde x, because the difference between a random variable x and a discrete value should always be a random variable. And a random variable should be uncorrelated with a discrete value. In this case, the estimated beta 1 hat is going to be unbiased and consistent, but the estimated standard error will be large. Because if we don't have any measurement error, then the standard error for the beta 1 will be smaller. And the measurement errors introduce more noise in the x and cause the standard errors for beta 1 hat to increase. However, since the estimated beta 1 is still unbiased and inconsistent in this case, we don't worry about fixing anything, because our primary objective for this course is to establish causal effect. In the third case, the measurement error stems from intentionally misreporting. Studies have found that people tend to underreport their income for tax purposes. If you were able to match the survey data with the individual's tax filing record, you will find that on average, people tend to report 10% less than their actual income. This means that we can model the reported income as 90% of their actual income. As a result, the estimated beta 1 will be biased upward by 10% as compared to the true beta 1. This is a special case when you know, based on the past literature, how much people tend to intentionally misreport on certain questions. And therefore, you can easily adjust the estimate to calculate the true beta 1 based on the degree of misreporting. The last case is when the measurement error is contained in y. In this case, there is a difference between the observed y and the actual y, as captured by w. Since the first least squares assumption is about conditional expectation of u given x's, not y's, the measurement errors in y does not result in violating the first assumption. Because in this case, the expected value of the error term given x is still going to be equal to 0. And therefore, the estimated beta 1 hat is still going to be unbiased and consistent. However, due to the measurement error in y, the variance or the standard deviation for beta 1 hat will be larger than before. But we don't consider this problem as severe. In most cases, we can even ignore it. So far, we went through 4 different cases of measurement errors. We could ignore the impact of measurement errors in the best guess model, and if the measurement errors are contained in Y, like in this case, because in both cases, the estimated beta 1 is still unbiased and consistent. But we do have to worry about the classical measurement error model, like in the case 1, and the case when people intentionally misreport the data, because both of those cases give rise to the biased beta 1 hat. Now, how do we fix the bias introduced by measurement errors? There are some ideas. The first idea, or the most intuitive idea, is to obtain better data. But empirically, this is something that is frequently easier said than done. The second idea is to model the process of how the measurement error affects the estimate. For example, if you understand why people misreport certain data, such as the amount of alcohol and drug consumption, and by how much, you can factor in the degree of misreporting in calculating the true beta 1. This procedure usually requires a lot of work and is hard to implement in practice. The last idea, or the most viable idea, is to use the instrumental variable regression, which we're going to cover by the end of this module. Now let's pause this video and do in-class exercises 5 and 6. Another source of bias comes from missing data in the sample. Formally, we call it sample selection bias. Depending on why and where the data is missing, the missing data might or might not be a problem. If the data is missing completely and at random, then you will have a smaller sample size, but your estimated beta 1 is still going to be unbiased. If the data is missing in your X variable, for example, you have some NAs in your X variable, then you can either reduce your sample size to get rid of those NAs or impute the NAs with some other values like the mean and median. In this case, your estimated beta 1 is still going to be unbiased. What is the most problematic is when the data is missing in your Y variable. In this case, the error term and the regressor are correlated, and this gives rise to the sample selection bias. Let's look at 2 examples to help illustrate why this is a problem. A very popular topic in the mutual fund literature is whether actively matched mutual funds outperform the hold market funds, or otherwise known as the index fund. In this case, the dependent variable on the left-hand side is the performance of various funds, either active funds or passively managed index funds. On the right-hand side, you could have a dummy variable that marks the style of the fund. The dummy is equal to 1 if it's an actively managed fund, or 0 if it's an index fund, together with a host of other control variables. This is a topic that is frequently fraught with sample selection bias, because the performance data on the left excludes defunct funds, or funds that had already died and therefore failed to voluntarily disclose their performance data to the database. It's arguably so that the actively managed funds who take higher risk tend to have a higher probability to flop. And therefore, the regression residual that contains all the dead funds tend to be correlated with the dummy variable that marks the style of the fund. When this happens, the estimated beta 1 is biased due to sample selection bias. The second example is when we regress wage on education. The wages of workers don't include workers who are unemployed. The unemployed workers having a wage of 0 are left in the regression residual. Since unemployed workers tend to have smaller years of education, the residual is also correlated with the regressor education. And hence, the estimated beta 1 is biased again due to the sample selection bias. In summary, if the data is missing your y variable, then your estimate beta 1 is biased due to sample selection bias. Here are a few suggestions on how to fix the sample selection bias. The first suggestion is to collect data that doesn't have the sample selection bias issue. Again, this suggestion is easier said than done. A lot of databases we use, such as the mutual fund and hedge fund databases, are based on funds that disclose their performance data voluntarily. It's not something we can control, and therefore we cannot obtain better data than what we already have in those databases. A second solution is to use randomized control experiment. Again, in our arena, this approach is difficult and is often unethical to implement. The last idea is to potentially model the sample selection bias problem. For instance, if you can figure out the unique attributes of the funds that are likely to go belly up, then incorporating these features in the regression, we can potentially correct the sample selection bias. The problem is that there are usually a myriad of reasons why funds go belly up. So it's hard to pinpoint the specific characteristics of these funds and incorporate them in the model. This approach is hard, and we will not do it in this course. In the end, we say that the sample selection bias issue is hard to correct. If you are missing value in the y variable, and therefore you have sample selection bias in your estimate, and chances are we don't have any easy fix for it. The last source of bias is called the simultaneous causality bias, or also known as the simultaneity bias. This is a very common problem in economics and finance. This bias happens when x affects y, but y also simultaneously affects x. For example, previously we tried to analyze how classroom size affects test scores. We found that smaller class size tends to be associated with higher test scores. However, it could also be the other way around. A district that has consistently produced higher test scores is likely to get more funding. And with more fundings, they help the school employ more and better teachers, which might help them reduce their classroom size over time. Another example is trade share versus GDP growth. Previously, we examined how trade shares impact on the GDP growth rates, but it could also be the other way around. Countries with higher GDP growth have more money to do trade, and because they're more naturally inclined to trade, the impact is mutual. Demand and supply is the same thing. If the price of the merchandise goes up, the demanded quantity will go down. However, on the other hand, if the demand goes down, the manufacturer might have to increase the price point in order to offset their loss, so the price will go up. Crime and police are also mutually causal. A neighborhood with a higher crime rate will likely have more police on the ground to fight a crime. But if the number of police on the ground increases, the crime rate will also likely to go down. Now let me show you the mechanism of how simultaneity affects our coefficient estimate. If we have a set of variables, say y and z, that are mutually causal, then we can use two different equations to show the relationship between y and z. The first equation regresses y on z and a control variable x and a random error term u. The second equation regresses z on y with the same control variable x with another random error term v. If we plug the first equation into the second equation by substituting y in the second equation and solve for z, then we have this equation here. What we're interested in exploring is that if the conditional expectation of u given z is equal to 0, if that is true, then the first assumption holds. Otherwise, the first assumption does not hold. Therefore, by rewriting this equation in terms of x, v, and u, we have this equation here. What this tells us is if the denominator is not equal to 0, and that if v and u are not correlated, then by definition, the covariance between z and u, as captured by this term here, is given by the coefficient for u multiplied by the variance of u. Furthermore, if gamma 1 and gamma 2 are both greater than 0, then the covariance between z and u is also greater than 0. Or z and u are positively correlated, and vice versa. In this case, it's easy to see that the first assumption is violated, and therefore the estimate for gamma 1 and gamma 2 are both biased. The ideas to fix simultaneity bias are to use randomized controlled experiment, which is not a viable solution to us, or develop a complex model to model the direction of causality, which is extremely hard to implement and is very rarely used in practice. The third solution is to use instrumental variable regression, which we'll introduce next. Before we move on to the next topic, let's talk about the sources of inconsistency for the standard errors. In this course, the source of inconsistency for the standard errors comes from heteroscedasticity. And therefore, to correct this problem, we talk about using the CSE function to create heteroscedastic robust standard errors. Another source of inconsistency for the standard errors comes from the zero correlation or autocorrelation in the error terms for the time series or panel data. This error stems from the fact that there is information overlap in the residuals over time. You will learn more about this problem when you take the time series analysis and panel data analysis after this course. The fix for this problem is fairly simple. Instead of using the CSE function, you will just use another formula on the standard error to correct this problem. Another important thing for you to note before we move on to the next topic is that the 5 sources of problem that bias our regression estimates are not considered problems in other areas of regression analysis. For example, if you are building a prediction model or a machine learning model, then your primary objective is to increase the predicted power of the model by making your R-square as high as possible. In those models, you don't worry about biased estimators. And therefore, what we have considered as problems in this class do not apply elsewhere.